start then.
I'd like to introduce, hey, pronouncing your name, Bruun, from University of Aarhus. He got his PhD in Oxford, studied with Nikos Nikopoulos. He's done a postdoc in NIST in Gaithersburg. He's also worked in the Nietbo Institute in Trento and latest in Lund. And he just moved to Aarhus where he works as a lecturer, right? And today he's going to talk about art spectroscopy, holograms and dipole interactions in cold gases.
Okay, thanks a lot. So, nice to be here. Nice to be part of this summer school. Sure. Yeah, so these are the three main topics that I will talk about today. So the overall topic is cold gases. So I will try and make some coherent introductions to the different subfields, so that people outside the cold atoms can follow what's going on. So the outline is, first I will talk about this class of experiment with radio frequency spectroscopy, which is a very important tool, experimental tool in the cold gas community. It's a tool with which they probe the effects of interactions. So I will do some theory for that, and then there's been people who were here last week have heard that there's been some discussions on tolerance and molecules and how they are coupled and how how the ground state, how they change from one state to the other. So I chose to talk a little bit about some reason we're going to take on that, and then if there's time, I will try to keep within the 1 hour time limit. I'll talk about the dipolar gases. So the first topic is the RF spectroscopy, or let me just give you a quick introduction to how you make strongly interacting gases in atomic systems. So in atomic systems, the atom-atom collisions, the particle-particle interactions are well described because you are at low energies, no densities. It turns out that you, for many purposes, don't need to know about the bare interaction. It's enough just to parameterize for the low energy properties the interaction in terms of one parameter, which is scattering length, which you can think of as the radius of these billiard balls bouncing into each other. So a good measure of the strength of the interaction in these systems is basically the scattering length divided by the typical interparticle spacing. And one of the neat things about these atomic gases, you heard it pretty much, I don't know how many times now during this workshop, is that you can use what's called Feshbach resonances to tune the scattering length. There's some hyperfine structure these atoms have, and because of that, you can utilize that to make the A, essentially, you can make the atoms scatter resonantly on each other, and that means that A goes to infinity, and within this two-body scattering picture, you make the interaction as strong as quantum mechanics allows. In the language of T matrices, for people who are familiar with that, the T matrix basically becomes unitarily limited. It scales as 1 over the relative momentum. So people have studied this both experimentally and theoretically, this ability to tune the interaction strength, so the interaction strength is increasing this way, and they have studied what's called the BCS-PEC crossover diagram, and you have a lot of funny physics going on here. This will not be the topic too much of my talk, but just to mention that you've seen these phase diagrams floating around where you go from a strongly interacting, weakly interacting BCS regime to a strongly interacting BEC regime. Actually, interaction strength is increasing this way, and you have all these funny phenomena occurring.
Sorry, Pierre, but does that actually, that imaginary unit, does it do anything sort of physically in the scattering matrix? Just curious.
Does it do anything physically? It actually corresponds to decay. Yeah. So the imaginary part corresponds to its interacting via a molecular state, which is decay. It can also become real if you make this one imaginary. If the molecular state is so actually it corresponds to above the resonance. The I survives, and you have decay of the molecule. below, when you tune the molecule below resonance, this becomes real, corresponding to a real bound state. So that's where this I comes from. That's a very short version. They can also play with the polarization, as you also heard. So they can tune not, if they have fermionic atoms in two different spin species, they can play with the polarization almost at will. So they can study the physics as a function of imbalance. So here's an experimental picture from a group at Rice University, where you are now going, I guess. So this is the majority cloud, and this is the minority cloud, and we see that you can really, there's a significant density imbalance, population imbalance between the two spin species. People have also studied this theoretically, this crossover, this phase diagram, not only as an interaction strength, but also as a function of population imbalance. You also heard this in earlier talks. This is a Monte Carlo study from the Trento group, where you get phase separation, you get superfluid, polarized superfluids, you get normal phases, etc., etc. And FFLO is, we've heard some talks about whether FFLO exists here or not.
So in these experiments, the interactions between the atoms, are they attractive or repulsive?
In this case, they can do both, but I think in this case they chose to be right at resonance. So that means that it's a strongly, they like to form pairs. So you can think of it as attractive. Again, I mean, they can tune around. They basically play around in this region here. Okay, so I don't know why. Okay, so, and we heard a talk last week by Martin Zwierlein from the MIT group, where he has then studied the extreme limit of basically one impurity, one minority atom sitting in a sea of majority atoms, and I'll get back to that. So this is all within this bigger program of studying these gases as a function of polarization and interaction strength. So that's sort of the experimental, what people are doing experimentally. One of the probes that they then, when they create these gases, and in fact, should probably, this diagram, these plots you saw here, experimental plots, these experimental plots, what Martin showed last week, this is what's called radio frequency spectroscopy. So that's the typical way they try to, this is a spectrum, radio frequency spectrum, and from that they try to induce what is the state of the system. That's a very common, powerful way of these systems. And how does it work? So now we get on to the first topic of my talk, which is radio frequency spectroscopy. Try to do a theoretical analysis on that. So the way they do it is that you have, let's say you have atoms you have trapped in a given hyperfine state 1. Then what you do is you shine in a photon that excites this atom to another hyperfine state, and this is it's called radio frequency spectroscopy because this frequency is because these are hyperfine level splittings is a typical frequency of the radio frequency. So you excite this, and as I said, this is what many of the leading experiments use. And what they do is, here's a typical spectrum. I also showed one in the previous slide. Here's a spectrum for the more balanced case. And what they've done is that they've varied the photon frequency you shine in with here, and then they see how much absorption there is. And you see these resonant lines, and they do it as a function of decreasing temperature. And you see that the line shape changes and it shifts. The position of the maximum shifts. And the interpretation of that is the following. For high temperatures, these are trap systems, so for high temperatures the trap is very dilute, it expands out, it has a lot of energy, so there are very few particle collisions, so you can think of this as just an atomic physics experiment. You have all these atoms sitting, and they have their hyperfine levels, and you just have to shine in the photon with the right hyperfine frequency, and you get absorption. So this energy they measure here is just a hyperfine splitting. But then when you lower the temperature, something happens here. You see, you get line shifts and you get a broadening. And that is because they of course do this experiment. These atoms sitting here are interacting. There's another spin species. This is two-spin system. The experiment concerns a two-spin system. So this atom here is interaction with another atoms in another state here, and these interactions change the line. Okay, so the interaction between these atoms here, and that gives line shifts. And that line shift, when you cool it down, the gas becomes denser and denser. There are more and more collisions, so that gives rise to shifts in the energy.
Have they populated 3 hyperfine states?
No, in this case they start with these two here, and they interact, and then they flip this one. And then they see how much energy you have to throw in to flip the spin of this one from this state to this state. But it interacts with this one, and when you cool down, the interactions become stronger and stronger with this one because the gas becomes denser and denser. So there are more and more collisions, and that gives rise to these line shifts here. And then the idea is, from these line shifts, to learn something about the interaction between these two spin states. That's the idea. And in this case, in the early experiments, people were very excited because they said, okay, this line shift here is pairing. You need to throw in more energy to flip the spin of the atom here from here to here, and that's because it's paired with that one. But of course, the story is much more complicated. It's not just pairing, and in general, these are messy experiments because, I will explain in the next slide. If you try to analyze these experiments theoretically, what you have to do is you have to calculate, at least within linear response, the transition rate of this atom flipping spin from here to here in the presence of interactions with this atom. You have to calculate the spin-flip correlation function. So it looks like that's the object you have to calculate. And that's complicated. This is a complicated problem to do because there are many things that play into the game here. There are self-energy corrections of this thing. There are effects of the trap. The trap is inhomogeneous. There are vertex corrections. I will get back to that. They are pairing. There are all these effects. So for instance, let me just give you an example of a misinterpretation in one of these experiments. So here's the previous slide. Here. So people actually thought that this double peak structure here was due to the fact that some of these atoms here, I don't know why it's gone, but some of these atoms that are sitting here are paired with another atom, and some of them are not. So you get some atoms which are not paired with this atom sitting here, and some of them which are, which gives rise to this double peak structure. And that turned out to be wrong. It was simply just an effect of the trapping potential. So these are complicated experiments, and many people have worked on this, the theoretical interpretation of these experiments. And here are some of the names, and I'm sure I'm leaving out some, but this is a big industry. And the bottom line of this, so this is yet another treatment of this RF spectroscopy, but the bottom line of this talk here is that instead of doing, in general, people are doing various approximations, and they're trying to one-loop approximations, etc. So we decided to, and that's not really in control of what is important in this problem. So what we tried to do was instead to take a limit where you have this atom with whose spin you're flipping, and then it's interacting with this bystander atom. We'll make this bystander atom very heavy, because then you can make a control conserving approximation. It becomes much easier. There's no recoil in the interactions. And you can actually derive exact analytical results in the limit of low density when it's very polarized. So there are not many bystander atoms, and you can then figure out what is, there's been a big deal about people whether you should include vertex corrections and what they do, and we will show that they're extremely important. So many of the initial studies which reflected that turns out to be questionable. And then we will also say that people in general associate resonance with large line shifts. This is not the case in general. And then we will also, comment on some of these commonly used approximation schemes, such as the data approximation. We will show that this is manifestly inadequate in this limit. It cannot reproduce these analytical results.
How about equal masses case?
That's much more complicated.
So, data approximation adequate, is inadequate?
That I don't know. I mean, this is what everybody works with equal mass case, and then it becomes very complicated. I mean, it's not because I'm a genius compared to other. It's just when you take the high mass limit, it's much easier. In that case, you can see that it's inadequate. But for the equal mass, who knows?
Do you mean that at present there is no theory that allows us to interpret hissing experiments?
a lot of people will. I mean, there are many theories that interpret these experiments, but they tend to be. It depends on who you ask. In some limits, they are controlled. For instance, if the final state interaction is 0, you can do controlled experiments, but in many cases they're not, because you have all these competing effects. I will get back to the best attempts for the equal mass case in a minute.
Can you remind us, 1 and 3, maybe it follows from this picture. 1 and 3 are interacting, and 2 is the one.
I should draw it. So I have my atom here. So initially I have them. These are the ones that are initially trapped. So these are interacting with each other. And then you want to probe those interactions by flipping up to that state. That's what you do. So you just look at that drawing. So this is the interaction you want to probe.
And so you said analytic results are available if on top of it, N3 density of 3 is much less than density of 1.
Mass.
But also density.
No, then I'll make the density of this one small also. So this has mass 3 and N3, and I'll make this small.
You will make them heavy and then less small.
Yeah. So it becomes a purity problem.
Density small. So it will be an imbalance problem.
Yes. Yes. And this is, yeah. Okay. Yes. That's what I do. So it's written here. So initially they're interacting with each other, and they have mass M and density mass M3 and density M3. I'll make this small, this one large, heavy, and dilute. And then you can do something which is controlled.
Oh, but can I also ask, so the species 2, they don't interact with 1 and 3?
No, they do.
Well, they
The
do, so
species
that's
2
the
interacts.
problem, right? Yes.
That's the problem.
That's why you need to look at this thing.
Yeah, that's the problem. Otherwise, you would just have, if there was just this interaction here, the 2 line would just be ideal gas. It would be.
Right.
People have looked at that, and actually now they're doing experiments where they try to turn this off. Then it becomes much simpler. Okay, so as I said, we will make these bystander atoms heavy, so they become static. Because then the thing reduces to just an impurity problem. So you can self-energy so the ones become a simple impurity problem. And also, yes, they can put in the self-energies, and that corresponds to this one-loop approximation. So just taking in self-energy effects in these spin-flip correlation functions is what people initially did. That corresponds to this one-loop approximation, but that's not adequate. I guess you all know that, because it doesn't obey the symmetries of the problem. And the symmetries of the problem you can easily see in the following case. If you make the interactions, this interaction equal to that interaction here, then, so you make the interaction of the bystander atoms with the initial and final state the same. Then when you do this RF flipping between state 1 and state 2, what it just corresponds to is just a rotation in spin space. You rotate the state of this atom from being in a pure state here and then to a combination of 1 and 2. But that rotation, if the interaction is the same, is the Hamiltonian is symmetric under that rotation, so that there's no line shift. Interactions don't play a role at all. And that is not obeyed by this one-loop approximation, as you will see later in the talk. It doesn't obey the symmetry. So you need to work a little bit harder to fulfill these symmetries.
Excuse me, York, I can ask you just a physics question before you will be describing the machinery, the physics, very simple question concerning the state of the system, because my understanding is, like in the case of polar and molecule, you have 2 states, two distinctly different states. Like in one case, you have an impurity, but this impurity can have one or no, or maybe more than one bound states, right? So you have a Fermi C, which is non-interactive, right? And then in terms of the single particle states, the impurity can create a bound state, or it can just create a potential which does not produce a bound state. And these are 2 different states. So,
Oh, you're talking about whether there's a bound state here.
yes, yellow and red.
I have no bound states.
You have no.
I have no bound states in this.
You presume that you have no bound state, or you can prove that you have no.
I assume that there's no
I
bound
see.
states. I simply
It might be
put
an
in-
interesting problem by the analogy with
Yeah.
polar and
That's a
molecule.
good,
It's just the limit in case of polar and molecule, and physics is the same.
Yeah.
Because you have just well-defined particles in the C, so you are supposed to have 2 distinct states.
That's a good point. Actually, we thought about putting in the bound states, but we didn't study that case.
Because then probably you will see some signature.
Yeah, that's right. I mean, there will be some poles here which should show up. You're right.
Do you mean that many-body bound state or two-body bound state?
Single particle, because the Fermi C is non-interacting. So the beauty of this, or simplicity, or whatever, of this problem is that there is a strong interaction between yellow and red, and no interaction between red particles. If you use Feshbach resonant, or just no for all practical purposes. So within Fermi liquid, well, under Fermi liquid theory, interactions are not even important. You have just a Fermi C of non-interacting particles. And you can, and the notion of a bound state is well defined, as opposed, say, to bosonic bed. So if you put an impurity in the Bose condensate, you cannot, strictly speaking, you cannot define the notion of a bound state, only quantitative. And here it's a qualitative difference, because they are well-defined particles.
Okay, so people have then tried to put in, and gets back to what people have done for the equal mass case. People have realized this and tried to put in these vertex corrections in the equal mass case, but it's a technically difficult problem, and they haven't really done it in a consistent way, but they've made attempts. So the state of the art for the equal mass case, I guess, is this paper here. People are interested, where people have tried to do it, but they haven't really taken in. They haven't summed the series essentially. They've just taken in one vertex correction. Okay, but here we can do it. It's much simpler because the momentum sums decouple from the frequency sums because there's no recoil. And what the physics that you're putting in is that you're putting in the fact that when you flip the spin, you have one hole. You create a hole here and a particle here, and that hole and particle you create in the same place, and they can scatter on the same impurity. And that's the physics. That's an important part of the physics that you're now putting in. It's the simultaneous scattering of a hole and atom in spin state 2 scattering on that impurity. And that is important because RF probes, they're localized in the same place. Okay, so let's do it. We sum the series, and we can do it because there's no recoil, and here's the expression. And we are doing this in a conserving approximation in the canon of Bain sense, so all propagators are addressed. And we do the frequency sum the usual way, blah, blah, blah. And we can do that. And we can do this for any density in 3. But in the limit, when we now turn down this density also of N3, actually we get back to an analytical, an exact result. Because then, to the lowest order in the density in 3, it's enough to put in the vacuum scatterings between, we don't have to put in any medium effects of the interactions of the bystander atoms with the atom who spin with flipping. So we can put in the vacuum expressions for the scattering matrix, because there's a density already out in front, and here's the expression. So this is a well-controlled limit of how this RF response looks. When these are heavy and they're dilute. It looks like that. And yeah, okay, so in the basic symmetries, you can see that when you put the scattering phase shifts to be the same, the effects of interactions disappears, and you just get back a Dirac delta function. You get back the non-interacting case, which is what you want. And what you can see is that the effects, so you're basically integrating over all energies of the initial state here, weighted with the Fermi function. This is the line shift without any interactions. Here's the effects of the interactions. And what you see is that it's described by a T matrix, essentially, which is given by the difference, the resultant phase shift is the difference in the phase shifts of the particle and the hole scattering on the same impurity. So that's the physics. That's because we put in this fact that the hole and the particle scatter on the same impurity. So the resultant phase shift is the difference between those two phase shifts. So that comes neatly.
I mean, I apologize, but is it possible maybe to explain it a little bit better? So, for example, well, maybe the easiest way, I think, for me to ask is, why do you expect this to be the ideal gas?
What do you mean?
So in case of tau1 or T1 is equal to T2, you should get the same D as for the ideal gas.
Okay, but that's so. If you start, let's say that you have the 1 and the 2. I mean, I haven't explained it well enough. If you have the 1, there should be a 3 here. If you have those two sitting in some interacting state, so they form some, they scatter on each other, and then they form some interacting state. Now you come with your probe that rotates between state 1 and state 2. You start rotating. The states that you started with, the many-body states that you started with, remains an eigenstate of the system because the interaction is symmetric. It doesn't care if you when you rotate this spin state 1 and 2, the interaction is commutes with that rotation. So the state stays an eigenstate. So it doesn't cost you any interaction. I mean, it doesn't cost you any energy, interaction energy to rotate it. You understand?
But should I think of N1? Should I think of N3 as essentially being just one atom of N3 in a sea of atoms N1?
Well, you should think of it
in the sense that, I mean, if there was some densities, there wouldn't be an ideal gas in some interacting states.
It is some interaction state. There is a line shift due to a finite density of N3s.
Okay.
But if the interaction between so there's a finite density, but if these N3s are interacting equally with this spin state and that spin state, doesn't care. The state doesn't care whether you rotate it because it remains an eigenstate. So you can think that if you for a moment ignore hyperfine splittings, it wouldn't cost you any energy to rotate it. You understand?
Okay. Okay, but maybe my question wasn't good enough. So then I'll ask the question. So now suppose those two guys are not equal to each other, then I would imagine that your answer will depend on what kind of state you had to begin with. Meaning, so you had this atoms 1 and you had this atoms 3, and they form some states.
Yes.
So wouldn't I see information about that state somewhere there?
Yes, that's what you.
Yeah, okay, but so it's just the formula is too simple to encode all possibilities, or I don't know, pick a particular possibilities of what they might do.
This is a simple formula where I've taken. I mean, the actual formula is this. I mean, it's more. It contains self-energy effects of the ones and so there are self-energy effects of the two. So there are encoded in the general result. There are encoded the many-body correlations between the ones and the threes. Now I've just taken the limits where I've taken the leading order in N3, and then it becomes this simple. Otherwise, these T matrices here, there would be effects of interactions in those. There would be effects of interactions in the density of states. I will give you the formula later. It's longer.
Okay, but should I think of this formula as, since it's a so lowest approximation in N3, should I think of it as essentially having very few of particles 3, and so they form some little bound states of polar or something like that, but otherwise the gas of ones is unaffected. And this is what this formula tells you. And then you start rotating ones into twos, and that's what happens.
Yeah.
That formula.
Yeah. So the formula is this simple.
Non-trivial many-body state.
What?
In some sense, there's no non-trivial many-body state. There's an ideal gas with some polarons inserted.
Okay, there's the effects. It's not an ideal gas of I mean, this is the first order effect of interactions on the line spectrum. If I start with an ideal gas, I just get this spectrum. Now I make this density finite. What? Then I see what is the first correction. Yeah. But then, I mean, this is the simple limit. I can also, I will give you the limit when N3 is not necessarily small. Then it becomes more complicated because then there are effects of interactions everywhere. This is just a simple limit N3 small.
Okay, and effect of interactions will be encoded in some function state.
Yes, density of states, self-energies.
And this thing will depend on what kind of states they'll form. The reason I'm asking is because I know if you have different than 1 and 3, and none of them are small, and if non-equal masses, you can get all sorts of possibilities and all sorts of phases and phase separations and all sorts of stuff.
This is not encoded.
This will be
No. I mean, the effects of the interaction between the 1 and the 3 is just. We just include scattering between the 1s and the 3s. There can be bound states, which you could
in this approximation, right?
That could be. You could put that in. We didn't study that case, but this is the effects of interaction between the 1s and the 3s is taken into account in this approximation. So that can generate a bound state if you want.
Right, but it won't generate some many more because it's an expansion of 3. Here, at this stage.
This is an expansion. At this stage, I skipped there's an initial state where I haven't expanded this to 3. I'll give you the formula. I'll show you. But there's no phase separation or anything built in. There's just the effective interactions is you allow them to scatter on the trees. You allow them to form ground states if you want. Okay, so we can just so this limit that I've chosen to focus on here was where I also expanded N3 has a simple. Basically, you're integrating all the atoms. The line shape looks like this. It's basically you're summing over Lorentzians. So you're summing over line Lorentzians. So the scattering energy of the one atoms that you're flipping from 1 to 2 has an energy E, density of states times the Fermi function. Then it has a line shift and a line width. And that line shift is given by the signs of difference of the phase shifts, and the line width is given in this case. And we like that because that is goes back to people have worried about. I never understood this. This is an old paper where he studied some classical gas with Boltzmann equations and things. But people have written down similar formula for classical gases scattering on each other. So this is a nice limit that we recover in the classical limit. But here it's a general result. The ones can be degenerate. And then if you do no vertex, you get the wrong result. So
these are formulas from the book. Excuse me, please. These formulas that you write down, delta, omega, and gamma, this is the shift of the line, and then the line width, and they're in the book.
Which book?
Soderman, Optics and Spectroscopy.
Okay, good. Yeah, we looked at for classical gas. We saw these. That's great. I mean, we found them in these obscure papers. Yeah.
Well, they are not obscure. It's nicely derived in the book.
Okay. Yeah. For which system?
Huh?
For which system?
Just atoms.
In the classical limit, right?
Yes.
Yeah.
Yes.
Yeah. Okay, that's I didn't know. We found them in these two papers here. This is actually by Stoof, Pink Stoof, this paper here.
Yes.
So that's why we started working on the
You
problem.
probably did not read the book.
Probably. I didn't read the book either. That's great. Yeah. Which book was it? Soderman?
Soderman.
Uh-huh.
It's a famous guy in optics and spectroscopy.
Ah, nice. Okay, so we recover the weak coupling results that the line shift is just the difference in the mean fields. And also we can read off from this formula here that resonance interaction corresponds to phase shifts of pi halves. That in general does not. So typically what people do is that they make this interaction here resonant. And that means that the phi 1 is actually pi half. And then they flip this to the upper state, and then they think, wow, the line shift is now really a result of these resonant interactions, and the final state interactions are not that important. But in this limit, you can see that that's not true, because if you put one of the phase shifts to pi halves, it just means that the line shape is totally determined by the remaining phase shift, but with a minus sign in front. So what the resonant interactions do is that the line shape is determined by this interaction here, but it's just shifted in sign due to this interaction here, which is resonant. It just shifts the sign. So then you're really reading off the effects of the final state interaction and not the resonant interaction. And then you can also see that you get large shifts when the phase difference in the phase shift is pi fourth, and that doesn't go hand in hand with large widths, which is when the difference in the phase shift is pi halves. Okay, so then here's the more general formula where I have them. So there are interaction effects here. So there are self-energy effects everywhere. These are fully dressed propagators everywhere, and also in these density of states. I haven't given you the formulas, but this is before this expansion in N3. So you have to expand this one in N3, this one, this one, this one.
What are these?
This is a density of states, including self-energy corrections, and these are T matrices, including medium effects. With fully dressed propagators. Okay, so then we just did some numerical results based on this self-consistent problem, so we determine everything self-consistently. And then we look at, let's see, what did we do? We look at, so let's make this interaction have a scattering length corresponding to a KF A2, so we make this have a given strength. And then we turn off this one initial scattering length, then the shape is like that. And then when you make the two scattering, the two T matrices the same. We recover the delta function, so we just did the full numerical calculation just because we could see how the line shapes took. And then now we make this interaction resonant. Then we see the sign of the phase, the line shape has changed compared to when it was 0. So this confirms this, that resonant interactions really changes the line shifts, and so it doesn't do much more. We also sort of studied an example of, let's make the final state interaction 0, but let's just make the initial interaction, we look at the line shape as a function of the initial interaction, and you can see that it, goes through, it goes through, first you make it stronger and stronger, so the line shift goes through a maximum when the phase shift is pi/4, and then it goes back when the phase shift is, when it's resonant, the line shift is not large, but the width is, and that confirms this fact that the line shift and line widths do not go hand in hand. Okay, then let's get back to this last point, which is recovery of this. In real life, these atoms have, the M3 is not infinite, it has a finite mass. So, for instance, if you trap potassium 40 and lithium 6, the ratio would be 1/7 or something. So it's a finite mass. So if they had to do the experiments, it would be nice to know which class of processes do you have to include to recover this impurity scattering limit that I've considered here. And it turns out, I'll just make the story short actually, that it's not enough to, so in general the masses are finite, the M3 and M1 have finite masses, M3 is finite, so you have to look at diagrams of this kind here and the corresponding vertex corrections. And it turns out that if you analyze these things, what do you have to do to recover this kind of physics up here? You have to actually include all kinds of permutations. You have to attach these lines in all possible ways to these loops here. Only in that way can you shrink this diagram to the correct limit. So what this tells you is that what this tells you is that if you want to study the limit of one atom much heavier than the other, you better go beyond that approximation. You have to attach all kinds of different permutations so that you can shrink it to get the right limit here. That's what I'm saying. Okay, so that's this part of the talk. So we made this conserving calculation, and we got analytical results in the limit when the density was low. And we saw that these vertex corrections can change the result qualitatively as compared to without them. And we saw what the effect of resonant interaction was. In general, it's not associated with large line shifts. And then we also saw that this latter approximation, to recover that limit, the latter approximation is not enough. And here's the paper if you want to read more. This is So let's jump to the next problem. This is a little bit more dangerous because this is the polar molecule coupling. So one of the people who studied this problem is sitting here. So we change gears now. So now we go to the polar problem where you have one minority atom sitting in a sea of majority atoms. Okay, and then people are studying this experimentally and theoretically. They increase the interaction, and then at some point, I mean, what happens is that, not surprisingly, it's just a fermionic quasiparticle in the beginning, but then when you increase the interaction beyond a certain point, it picks out one of these majority atoms, forms a molecule, and then it becomes a bosonic quasiparticle. And people call this the polar one, and they call this the molecule. And this has been studied experimentally. So there are these R spectra here, as I showed you on the other slide also, we saw last week. The people have seen this transition from a fermion quasiparticle to a bosonic quasiparticle, polar to a molecule, when you increase the interaction. And they have measured the energy. This increased very well with Monte Carlo calculations done by Boris and Rafakov here, and also with variational functions. So a lot of people have worked on this, and the transition. What I will focus on here is the transition between this molecule and the polar one. What happens? Okay. I will focus on this sharp transition here. So here you see the fermionic quasiparticle residue. This is a theoretical calculation. It's supposed to drop abruptly to 0. And I will focus a little bit on that coupling between the polymer and the molecule. And what I will just say is, the bottom line is, in the last 15 minutes here, is the leading process coupling a molecule and a polymer is a free body process. The transition is sharp, and phase-space and Fermi statistics strongly suppress the decay. So it's not an avoided crossing; it's a decay. And we discussed this. And you can have very long lifetimes. So that you could actually measure, should be able to measure this experimentally, this decay. So what we're doing is, we are focusing on this region here. So here's the polymer energy. This is taken from your paper. And here's the molecule energy as a function of interaction strength. And we focus on this region when they cross each other, where the energies are more or less the same, zero momentum energies are more or less the same. And we will figure out what is the coupling. Okay, so first, we note that a P equals 0 polymer if we're sitting here, so it's not the highest, lowest energy anymore, it can't just decay into a P equals 0 molecule, because then it creates a zero momentum hole also, but that zero momentum hole is in the middle of the Fermi sea, it's too expensive. So that process is not allowed. You do not have enough energy for that. That's why it's a sharp transition. So you don't have an avoided crossing. They are not coupled directly, the polyron, zero momentum polyron and the zero momentum molecule, because it requires creating a hole in the middle of the Fermi sea, and that is too expensive energetically. So what we have to do is, the leading order is instead, if we look at the polyron decay, what it has to do is, it has to grab one of the majority fermions, form a molecule, but then it has to create an additional particle hole excitation in order to conserve both momentum and energy. So this is the leading process here, and for the molecule, it's vice versa. If you're sitting here, the molecule wants to decay. P equals 0 molecule wants to decay, sitting up here wants to decay down. It has to release the majority atom outside the Fermi sea, and then it has to create an additional particle hole excitation to conserve both momentum and energy. And it's those two processes that gives rise to the couplings and to the decay. So we calculate this, and basically what we do is, we do a hole expansion. Let's focus on the polyron. We do a hole expansion in the polyron self-energy. This is in the same spirit of these variational calculations that work reasonably well. So we do the same. And the processes which involve one hole in the majority Fermi sea, that's just the usual ladder approximation, gives no decay, it just shifts the energy, it gives no damping. So we have to look at processes which involve two holes. So what these processes correspond to is basically that the polyron is coming in, it scatters, and it forms a molecule, and it has two holes and one particle. And there are two, at this level here, I've written two diagrams here because you can swap the whole momenta. There's a Fermi antisymmetry built into this problem, and that gives rise to strong suppression of the damping, as we will see. So here is the polyron, and here's the molecule. And it's likewise for the molecule. We look at the molecule, so we have to look at the molecule propagating in a vacuum. It's given by this kind of propagator here, where you create the molecule in the vacuum state. We take you work in a single channel model because we have broad resonances, so it's basically the Yukawa wave function for the molecule. We look at the molecule vacuum propagator, but this one can decay. It can couple to the polyron. Here's the polyron, creating two particles and a hole. This is exactly this decay of the molecule. So this is the process we consider. And we also have to figure out what is the matrix element coupling the molecule and the atom. We can read that off from all this, because basically the molecules and the atoms couple via the T matrix, so we can read off what is the coupling by, you can read that off from these kind of analysis here. What the appropriate matrix going to be is to put in between this molecule atom coupling here and this black dot here.
Meaning that you just truncate the expansion and make it self-consistently gives you everything, right? So you do not put any ansatz, like Shevil ansatz by hand. You just truncate the series.
I truncate the series, yeah. Yeah, but it's the same, I guess.
Yes, it's the same,
it's
because
the same.
What we were doing numerically, we were also calculating the series up to some high enough term.
Yeah.
So basically truncating the series is absolutely equivalent to Shevil's.
Yes. Which is truncated actually at two holes. We didn't go beyond that. So yeah, so we let's focus on the polyron decay. So we calculate the imaginary parts of these things. And what you end up with when you do this analysis, again, it's very easy to do because you have basically the majority atoms form an ideal gas. So you can do these frequency sums very easily, and there's no population of the spin-down atoms, so it's very easy. It simplifies things significantly. So you end up with this golden rule type of expression for the decay of a polaron. You are summing over the exit hole momenta and the exit majority atom. You're summing over all the k's, and you conserve energy. And the resulting molecule you create is given by the sum of the two hole momenta and the sum of the particle momentum, so that you conserve momentum. So this delta function expresses both. This expresses energy conservation, and then the matrix element squared is given by this function here, which you can read up here. So you basically have to evaluate this expression here to get the decay rate, and we've of course made a pole expansion for the molecule to get the decay rates. So just phase space, if you just look at phase space effects, how would you expect this decay rate to scale with frequency? Well, the usual arguments give you that you are integrating over free energies around the Fermi surface. This is for low temperatures. This gives you an omega to the third. But then you have an additional molecule momentum here, which gives you an additional omega to the... there's something wrong here. Integration over the two... Oh, the integration over the two hole momenta gives you omega squared, and then you have omega to the 3 halves from the molecule. So the remaining energy is determined. So you get this energy scaling here. So you already see now that the decay is highly suppressed. It's a very high power in the energy difference. So when the energy difference between the particle and the molecule is small, this is small decay rate, simply due to phase space. And the matrix element, then there's this Fermi antisymmetry. You can swap the exit hole momenta, and that gives you an additional damping. And the way it works is the following. Because you have to create a molecule with very low momentum, small momentum, you basically have that the outgoing particle and the two outgoing holes have to sum up to approximately 0 momentum. So they essentially form this triangle around the Fermi surface. And in particular, it means that the angle between the two hole momenta and the particle momentum is more or less the same. And that gives that you have to basically, since the matrix element only depends on if the angle is the same, this matrix element goes to 0. It corresponds to that you have Fermi antisymmetry. When you swap the two hole momenta, you get an additional factor of frequency. So you end up with a damping rate that scales with omega to the 9 halves. So this is, as I said, a very slow damping rate, and it's a result of Fermi exclusion and phase space effects. And the same with the molecule. It's the same. It's very slowly decaying. And here's a numerical calculation where we try to calculate this expression. And you very nicely see this is an expansion result around small energy, and you see that when you increase the energy, the rate goes up with this power here, to the 9 halves, when you just calculate the same numerically. So this is the basic conclusion of this part of the talk. Is basically if you have a polaron and you sweep it here, it's a ground state, but then you change the magnetic field so the scattering length goes over here. It can decay, but it will decay very slowly. If you plug in numbers, time scale is up to 100 milliseconds, and you should be able to see that in the RF spectrum.
Talking of numbers, am I right that your conclusion is that because of this purely numeric effect of narrowness, because speaking theoretically, the two guys would be well defined only, both of them would be well defined only close to the transition point. But because of this narrow distance of the wave, am I right that actually both lines are well defined just within the whole plot? Can you explain that?
That's what the formula gives us, at least. I mean, if you plug in, I think this difference goes to omega is equal to EF half. I mean, in the limit, the difference becomes the Fermi energy half.
Oh, when you go away, definitely. But just if we just discuss this particular plot where the distance between two lines is small for some numeric reason. Because I don't know why these two lines just go pretty close to each other. Actually, it's very unfortunate because experimentalists cannot tell one from another, unfortunately. So experimentalists just see one in the same line, which is not good enough. But on the other hand, if the two lines are pretty close to each other, you have small delta omega, and this delta omega gives you the scaling.
Yes, you're right. I mean, you're right that if you plug in the numbers in this, you get long lifetimes in this whole plot here.
Mm-hmm.
What I'm saying is that when you go way away, you get other processes happening. Then delta omega, the energy difference becomes large enough, and you can create direct transitions. But you're right. If you just plug in these numbers here, you get long lifetimes.
Because that's what we were. You see, just the very fact that we were able to see two distinct lines numerically means that they're both well defined. Otherwise, we would clearly see that one Green's function, say, bipolarly gives a pole, and the other one gives nothing.
Actually,
with our numeric accuracy, we see both poles in both functions, meaning that we were not able to see numerically the width. It was so small.
Actually, that's why we started this problem, because we studied your paper. We couldn't understand how you could do it numerically, how you could find this line when it was not the ground state with Monte Carlo.
Because the width is so small that you cannot even resolve it numerically.
Yeah.
You can resolve the distance between the lines, but not the width.
Yeah. And you also wrote these space arguments.
That's why the space argument was there. So we clearly, we definitely knew that when we approach the critical point, both lines will be well defined. There is a phrase in the paper about the space argument itself, but in terms of the numbers, we didn't know how long can we go.
That's why we started this, because we studied your paper. So this is a brute force calculation of those phase-space effects.
This one's from the heavier stuff.
Okay, so here's the conclusion. So the leading process is the three-body. The transition is sharp. Phase-space influence statistics makes strongly suppressed decay, making it very well defined, and the lifetimes are the order of the milliseconds. There's a third part of the talk, but I think maybe I should stop here instead of going on. I can just give you basically, I can skip a lot of slides and then just give you a 10-minute version of. This has to do with dipoles, which is something we are working on, and I think Joris Skarpnikov will talk more about. This is a new trend in the cold gas community, is that they trap molecules or atoms with a permanent dipole moment, and the dipole-dipole interaction, two dipoles repel each other if they sit next to each other, and they attract each other if they are aligned like that. So your interaction becomes anisotropic, and it's long range, at least in low dimensions. It scales as 1 over r cubed. So you now have new systems with this kind of interaction here, and there's a big push by several groups to study these systems. And I'm just going to advertise, basically what we did was, there's an instability built into this problem, because the interaction is 1 over r cubed, and it's attractive when they're aligned head to tail. So the thing can collapse, the kinetic energy cannot beat this 1 over r cubed. So what people then speculate doing and trying to do experimentally is to suppress, to make the system low dimensional. So in this case, I've drawn a two-dimensional system where the dipoles are aligned by an external field. And then when you align them so that they're perpendicular to the plane, they always repel each other, and you should see no collapse. So people are planning to study low-dimensional systems in order to stabilize this collapse. And we studied, in this case, then a two-dimensional system of dipoles, where we will vary the angle here, and we also vary the dipole moment d squared.
So I just want to add, June Gale already has the setup as of right now.
Who?
June Gale, Boulder.
Okay, I never seen any publications for this. But
Well, I think he hasn't published it yet, but
experimentally,
experimentally, he's an experimentalist. So he already has this very setup.
with many layers or just one
I
layer?
think it's many layers as this pancakes. You know, one-dimensional layers in one direction.
Yeah, but what they're going to do experimentally, they're going to get rid of many layers and have one layer or two layers. That's what they gene cells.
Well, my understanding is that they'll just suppress tunneling. They'll make them into very well separated layers. Yeah.
Yes, but this, you know, the fact that they suppress tunneling does not mean that it's equivalent to one layer, because because the dipole-dipole interaction is one branch.
Sure.
The dipole-dipole interaction between different layers plays a role. Yes. So therefore, there is a difference in between many pancakes and one pancake or two pancakes. Yes. Okay.
Yeah.
And what they also have experimentally is that in their case, the dipole is perpendicular to the plane of the pancake. Yes. Which allows to suppress instability quite nicely.
But they can change this angle if they want, I guess.
Yes, they can, but there are additional difficulties. For example, if you speak about bosons, it's hopeless in the present case. Yes,
because they collapse.
The thing is that it's hopeless because of a very simple reason. That in real life, the motion is not exactly 2D; it's quasi 2D. You have 0-point oscillations in the perpendicular direction, and then what happens is that the amplitude of 0-point oscillation is fairly large, and molecules still have a possibility to go like that and then undergo this terrible chemical reaction. In the case of fermionic molecules, there is an additional suppression because they only undergo P-wave scattering. It's easier. Yes? And what the hope is at GR is to reach the stability in the case of fermionic single component polar molecules.
This is exactly what we studied. So I'll just give you this is taken from so we studied the state of this system as a function of the dipolar strength and also the angle. So there has been many papers, and after we did our work, there has been many papers, I guess you will talk about some of this later, about stripe faces and many pancake layers interacting. What we study here is we study collapse instabilities and superfluidity for just one layer as a function of the angle. And you can see that when you tilt the angle, you start getting attractive regions inside the layer. Two dipoles sitting here will attract each other, two dipoles sitting like that will repel. So you can start getting, either they collapse, they will all line up like this and collapsing, or they will form bound states. And I'll just flash the phase diagram. I'll just do this slide here. But what we did was, and then I will stop, I think. This is the main result of our study. We find that as a function of the dipolar strength, there's a superfluid region where actually the system is a p-wave pair. It forms p-wave Cooper pairs like that, just as in the 3D case. But then when you increase the dipolar, we calculate the compressibility of this system. And when the compressibility becomes negative, it's a sign that it's not in a metastable state anymore. It collapses. But we studied both instabilities, the superfluid instability and the collapse instability, and we find that the system is metastable towards collapse in a region where it can be superfluid, where it can be a p-wave superfluid. So there's a large region in parameter space in this phase diagram of angles and dipole strength where it's superfluid without collapsing. It's in a metastable state. And we also calculate, it's a two-dimensional system, so we also calculate the Brzezinski-Kosteles-Saulis transition temperature as a function of the angle and as a function of the dipole strength. And the details are given in the next slides, but this is essentially BCS theory with some PKT, the theory of Bach-Wiener temperature, and this is just calculating the compressibility within a Hartree Fock. That gives you that phase diagram.
So is that like Fermi liquid instability at 0s or something?
It's like it's basically the compressibility. It means that the compressibility goes negative.
Can I think of it in terms of weak coupling Fermi liquid?
Yeah.
Instability?
Yeah. Basically, you're calculating the energy in a sort of a Hartree Fock simple calculation. What you do, there's a slight complication. The Fermi surface becomes deformed. It becomes elliptical because it's a dipolar system. So the Fermi surface is not spherical anymore. It's an ellipse. But that's a slight complication.
The only thing is that when you get a collapse, yes, so you have an angle, yes, and therefore you get attraction.
Yeah.
Then the value of the parameter K Fermi multiplied the dipole-dipole distance, which is dipole moment in the square multiplied mass, is larger than 1. And none of these mean field approaches work in that case. Yes. That's what you should be aware of.
Yeah, it's the first shot at it's a very simple mean field calculation.
Yes, and then, but you know, the mean field calculation is okay in the BCS regime, yes? As soon as you calculate the scattering amplitude correctly, that's what you should do, yes?
Yeah.
At the end, it's okay, yes? And then in the in the BCS limit, the Kosteles-Tauler transition temperature practically coincides with the BCS transition.
Yes.
The relative differences.
You have the
just
difference here.
divided by
This is
factor
the
of-
Kosteles-Tauler.
Yes, yes, yes.
And
yes,
this
yes.
is BCS.
Everybody believes that. Everybody knows that.
Yeah.
From a long time ago. But
Oh, you
here,
have to calculate still.
when you go to, let's say, larger KF, multiply the characteristic distance, dipole distance, then the mean field approach breaks down. Yes, and this is the region of collapse. Therefore, one can only say, roughly speaking, when K Fermi multiplies dipole distance is of order something like 2 or 3 or whatever it is, yes, then there is a collapse. But this is the region where the mean field approach is not valid.
Yeah, but it would be, at least it's nice to see that it gives, for the weak coupling regime, where you would expect the Hartree-Fock to work, that it doesn't give collapse. So this is what this tells you. That it's at least it's self-consistent for weak coupling, that it is superfluid without collapsing.
Well, weak coupling, yes, I agree, as long as you calculate the scattering amplitude correctly. I will explain you details later, yes, because I had a look very recently. I just happened to have a look in what you have written on there.
Wait a minute.
So how do you calculate Kosteles-Tauler?
Like I was the first time, sorry.
Oh, sorry. Sorry.
So my question was, so if we have fermions without hard core, I believe it's a theorem that the system can be only metastable because when we go to high density, the potential energy scales with a higher power than the Fermi energy. And whenever we have a system without a hard core, it's guaranteed to collapse, and it's only a question of metastability,
It's a
complete and instability. So I believe that for a dilute system, we just need, the physics is very simple. Once you see that you have a potential without repulsive hard core, the system is guaranteed to collapse.
The reason is that when you are in the dilute regime, and that's where heat is in the left-hand side, yes, then the Fermi energy, the kinetic energy, beats everything, yes.
Unless you have a dense drop. So that's
Just a second, just a second. Therefore, of course, what you can do, you can make a plot of the energy as a function of the density. Then what you will see is that the energy increases with increasing density, reaches maximum, and then drops.
That's what I
And
call
there is a very large barrier. Yes. And then what he is talking about, and not only him but also some other people, I will not tell you who these people are.
Find out what's wrong with it.
Yes. So what he is talking about is this region where you are to the left first, yes, or to the right. Sorry.
To the right.
Yes, to the right, where the system is perfectly stable. The barrier is huge. Yes, but then what he is also saying, and not only him but also other people, is that there is a collapse when the energy reaches maximum. It then drops down. Yes, and that's what he calls the collapse. And this is his region to the right hand side.
Absolute instability.
Yes.
Oh, I see.
And that's what he said.
I see.
But what I told him is that
No, I got your point.
yeah, what I only told, I perfectly agree with the physical picture. Yes, what I only told are two things. First of all, when the collapse occurs, these are large densities. It's not the dilute limit anymore, and this mean field approach doesn't work, strictly speaking. Therefore, qualitatively, we understand that it's something more or less like that, and so on. Yes, then, what I told him also some other thing, but this thing is not for a general audience. I will explain George later. That when he deals with the weak coupling regime, yes, then, in order to retrieve nicely the BCS transition temperature or the other parameter at, let's say, at zero temperature or whatever, he has to calculate the scattering amplitude very nicely and very correctly, which is a big deal.
Have people done this?
Yes, I will explain.
Because that's what we thought about doing first, but we couldn't find. This is new, no?
Yes, this is new.
Ah, okay.
Yes.
Awed by this brilliant display of deep insight, I forgot my original question.
I'm sorry for that.
Oh, that's okay. It was very enjoyable.
diagram is a stability diagram based on mean field calculation.
Yes.
How about the stability against chemical reaction? Is this fluid species still stable against chemical instability?
What do you mean with chemical reaction?
What was the real chemical reaction?
What?
KLB, undergo chemical reaction to K2 plus alpha. In this is the mean field calculation.
Yeah.
But maybe actually what might happen is that KLB and KLB undergo chemical reaction to K2 plus alpha. K2 plus alpha.
Mm-hmm.
So how about the stability? Have you investigated this kind of stability against chemical reaction?
No, but that requires free body. Is this a free body process? Or
That's the problem.
this is free body. No, we did not investigate that. So you have two reacting chemically, but how do they get rid of the energy?
So I think it should be relied on quantum chemistry. Yeah. So, but that channel was not taken into account in the usual calculation.
No.
But it seems that, and that's happening. Yeah. So I am curious whether usually mean field stability calculation is relevant for other systems. But my question is whether that is still relevant in this polar molecule.
Okay. Let's talk about that. No, we did not consider this chemical cold chemistry part.
Yeah, but the cold chemistry part is very tricky, you know, and there is a recent calculation. I think that Jeremy Hudson was involved, the guy who is a great chemical physicist. In the end, it turns out that for many molecules made of alkaline atoms, like potassium, rubidium, lithium, cesium, all molecules which include lithium, the chemical reactions are present, and this is terrible. But on the other hand, if I take alkaline atoms, different alkaline atoms, and form a heteronuclear molecule, there are molecules which do not undergo these chemical reactions. I think it's like sodium rubidium or something like that.
Lithium cesium.
Yes, and there is a recent paper of Jeremy Hudson and I think John Bourne and someone else, yes, where they write that. You know, I am not responsible for these calculations. Because, you know, I can understand what chemical physicists are talking about, but I'm not responsible for the results. But at least the name of Jeremy Hudson is such that usually he does correct calculations. Yes, so, and there is an information that, let's say, 60 or 70% of the alkaline atom molecules have these chemical reactions, and there are 30 or 40% of this type of molecules which do not have that. Yes. Therefore, in principle, from a theoretical point of view, if we are discussing these dipole systems, we are allowed always to say, okay, let us consider these 30 or 40% which do not have these chemicals.
Okay. Yeah. But how about KRB?
Huh?
KRB case.
What?
KRB.
Potassium rubidium, they do have chemical reactions. And this has been measured. And this is really terrible for the present experiment because, you know, and, okay. Lithium cesium, which has also been produced in Heidelberg by Matthias Weidenmüller. These systems are also expected to have these terrible chemical reactions. So,
how serious?
Huh?
How serious?
Well,
can you be serious?
I think they're about the same serious as in the case of potassium rubidium. What it means is that for realistic parameters, if you have these, the system that George is considering, then, let's say, making fermionic molecules is okay, yes, and then you may reach stability. Making bosonic molecules, you have to confine them very strongly and so on in order to forbid the approach at short distance. So there is a problem with bosonic dipoles. With fermionic dipoles, I guess, even in these systems like potassium, rubidium, lithium, cesium, they can undergo difficulties. Yes.
I would also imagine that it all depends on theta. If theta is private too, they cannot approach each other.
No.
So the question
What happens is, wait, I agree with you completely. If we work exactly in the two-dimensional case, I would say yes, you are right. But what they do, you are never exactly in the 2D case. Particles undergo oscillations in the third direction. Therefore, what happens? They go like that. They approach each other, and when they approach each other at short distances, the relative motion is three-dimensional. It's equivalent to 3D.
Yes, but they have to overcome a potential barrier to approach each other.
Yes, but
It's all has to be calculated by people at some point.
yes, and then what they say that for bosonic molecules it's terrible.
Okay, what is a fermionic molecule?
For fermionic it's easier. But I think we should turn to the speaker.
Finish.
I heard this story, which essentially one-to-one story from Misha Baron. Is he part of your group or completely different?
There's a meeting there.
Yeah, but